Hello there, and welcome to Sleepy Earth, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're drifting into a question that's as ancient as the oceans and as wide as the sky, and yet it's one most people never think to ask. It's a question hiding in plain sight, lapping at the shoreline, swirling in your teacup, clinging to your windows after a rain. Where did all the water on Earth come from? It's funny, isn't it? Our planet, this pale blue, feels so naturally watery that we start treating it like background scenery. Oceans that cradle continents, clouds that hush across the sky, rivers that braid the land like silver thread. It all feels ordinary, but it isn't. Water is rare in the way we experience it here. Liquid, abundant, stable, life-giving. The seas feel eternal, like they've always been waiting for us. But they had a beginning, and that beginning might be older, colder, and stranger than you expect. So before we drift into cosmic dust and ancient stones, let me ask you something softly. What time is it where you are? Morning coffee? A quiet afternoon? Or the hush of midnight rain? Wherever you are, I'm glad you're here. And if this kind of slow wonder helps your thoughts unwind, if it brings a little calm to your window of time tonight, I'd be grateful if you liked the video, subscribed, or shared it with someone else who's floating through curiosity with sleepy eyes. Now, settle in. Let your shoulders drop. Let the day loosen its grip. Because in Earth Story, water is both the ink and the paper. And to find its source, we have to sail beyond the sky, across time itself, back to a moment before there was even a sea to remember. Roughly 4.6 billion years ago, Earth was born not as a gentle blue marble, but as something brutal, a fireball, dry, molten, merciless. No oceans, no rain, no calm shoreline, just heat, violent, glowing, restless. And yet today, more than 70% of Earth's surface is covered in water, liquid water, a delicate, rare, life-giving phenomenon. So, how did it get here? Was water always part of Earth's makeup, hiding inside the planet as it formed, tucked into its molten heart? Or did it arrive later, delivered by icy messengers from deep space? Tonight, we follow the water story. From interstellar ice to deep mantle secrets. From violent impacts to gentle rains. Because to understand where Earth's water came from, we need to go back. Way back. Before oceans, before rivers. Before Earth even had a stable surface. Back to the beginning. And strangely enough, part of this story begins somewhere quiet. In the cool, quiet vaults beneath Honolulu. Inside a building that could pass for just another university annex. A tiny fragment of Earth's deep memory once set off a chain reaction of questions that reached all the way to the stars. The year was 2014, and a team of geochemists led by Dr. Lydia Halleys was studying microscopic inclusions inside an ancient basalt rock, a relic from Earth's early mantle, brought up by volcanic forces. Inside that rock were tiny trapped specks, little pockets of glass sealed inside the mineral olivine, and those specks carried something precious. Not treasure, not gold, something rarer. Isotopic fingerprints, clues, whispers, chemical signatures from a time when Earth was still assembling itself. And inside those signatures, they found something strange. Deuterium, heavy hydrogen. The ratio of deuterium to hydrogen, DH, works like a kind of cosmic signature. Different sources of water across the universe carry different ratios, like different accents in a language spoken by molecules. So Halleys and her team measured the DH ratio in those mantle samples. And what they found was this. The DH ratio down there, deep inside Earth, was much lower than the DH ratio in our oceans today. Much lower than the signature carried by comets. And here's the part that made scientists sit up straighter in their chairs. That low DH ratio closely matched the ratios found in certain meteorites, especially carbonaceous chondrites, primitive, ancient space rocks, the kind of objects that have been drifting since the early solar system, holding on to chemistry like a time capsule, a tiny chemical difference, and suddenly a window cracked open, because in that moment, one possibility grew louder. Maybe Earth's water didn't come mostly from comets, like people assumed for so long. Maybe it came from something older, something stonier, something built into the planet's own origin story. But to make sense of that, we need to understand how Earth formed, not as a calm miracle, but as a storm of stone. The solar system was born in chaos. A rotating disk of gas and dust swirled around the young sun, hot, turbulent, glowing. Within that disk, grains of dust began to stick together. Tiny specks became clumps. Clumps became collisions. Over millions of years, they formed larger bodies, planetmals, protolunets. It wasn't graceful. It was a cosmic demolition derby. Gravity was both the hammer and the glue, and our Earth began as one of those growing bodies, a ball of rock and metal, built from countless impacts, stitched together from smaller pieces. Some of those pieces carried water, not oceans, not rainstorms, not puddles. This was water trapped in minerals, bound tight inside crystal structures of silicate, hidden in dust, locked away like a secret. Hydrated minerals formed out in colder regions of the solar nebula, far from the sun's warmth. And over time, those materials drifted inward, nudged by gravity, pulled by migration, scattered by the restless choreography of early planets. When those wet, rocky bodies slammed into growing Earth, they didn't deliver water in bottles. They delivered it in bursts of steam. And here's the paradox. Early Earth was hot, really hot. Hot enough to vaporize anything wet. The surface was molten. The air above it, if you could even call it that, was like a temporary shroud of rock vapor and volcanic gases. So how did any water survive? Some didn't. A lot of water delivered early on was likely lost, boiled off into space, stripped away by solar wind, or blasted off by impacts. Earth was being battered constantly, and anything light and easy to escape often did. But not all the water fled. Deep beneath the surface, some found refuge, locked into minerals, pulled downward, carried into Earth's forming mantle, hidden away where the heat was fierce. Yes, but where the gravitational grip was strong and the chemistry could hold it. And as Earth slowly cooled, as magma oceans began to settle, as the first crust tried to form, the planet started to breathe. Volcanic outgassing began to pour gases into the sky. Steam, hydrogen, oxygen, carbon dioxide, and water vapor. And eventually, when the surface cooled just enough for the vapor to condense, the rains began. Not gentle rain, not romantic drizzle. Torrential storms, sheets of water falling for thousands of years. Rain that turned fire into ocean. And if Earth's water came mainly from those water-bearing planetimals, those carbonaceous chondrites, then maybe Earth was always destined to be wet. Maybe the ingredients for oceans were baked into the recipe from the start. Not blue at first, not calm, but damp deep down, waiting. Still, there's another character in this mystery, one that's hard to ignore. Those icy comets, streaking through the dark like messages from the outer edges of the solar system. For decades, comets were the prime suspects. After all, they're packed with ice. What could feel more intuitive than icy visitors from the Kuiper Belt or the distant Oort cloud crashing into early Earth and melting into seas? And yes, early Earth was hammered relentlessly. Around 4 billion years ago, the late heavy bombardment was like a cosmic storm of rock and ice. If comets were going to flood the planet, that would have been their moment. But when scientists actually measured their isotopic fingerprints, their DH ratios, something didn't line up. Most comets have too much deuterium. Their water is close, but not quite, like a puzzle piece that almost fits, but refuses to click. Some comets, especially ones closer in, tied more to the asteroid belt, come a bit closer to Earth's ratio. But even then, the match isn't perfect. And even if you add up their potential contribution, it doesn't seem like enough. So maybe comets weren't the great source. Maybe they were a minor drizzle, not the flood. And maybe the real couriers of Earth's oceans were those ancient meteorites, carbonaceous chondrites, small, stubborn, water-rich stones that helped build the planet itself. And if that's true, then every ocean wave is made of molecules that once rode through space, bound a rock older than Earth. And that is where we'll continue drifting in the next part, back into the Hadean world, where fire and storm learn how to share the same sky. Before the seas churned, before clouds even had the breath to gather, Earth was still a smoldering question mark, spinning in the newborn solar system like a coal pulled from a cosmic furnace. Try to picture it not as a world, but as a process. Not continents and coastlines, but heat, motion, collision. A molten sphere, faintly red, as if the planet itself had an ember-lit pulse. Its surface wasn't solid, not yet. It was a restless ocean of lava, constantly stirred by impacts, constantly reshaped by its own violent infancy. Earth, in its earliest millions of years, wasn't a place you could stand. It was a place still becoming. And in that version of the planet, water, if it existed at all, wasn't something you could drink or swim in. It was more like a ghost, a chemical whisper, a molecule waiting for the world to cool enough to hold it. Back then, the atmosphere wasn't the gentle blue blanket we breathe today. It was thick and choking, more plume than sky. Volcanic outgassing pumped it full of carbon dioxide, sulfur compounds, and silicate vapor. If you had stood above that early Earth, somehow your eyes wouldn't have seen a horizon, just haze and heat. A world wrapped in its own exhale. And there were no stable continents. No green. No soil. No coastlines to soften the edge of the unknown. Any land that formed was temporary. Crust that cooled for a moment, then cracked again, swallowed by fresh magma, or shattered by a new impact from above. Because impact were common, not occasional events, but part of daily planetary life. Earth was still growing, still sweeping up leftovers from the solar system construction. Some impacts were so massive they could melt whole regions, like dropping a hammer into a pot of glowing metal. And one impact, the famous one, may have changed everything. A Mars-sized body, often called Theia, is thought to have collided with a young Earth, ejecting a cloud of debris that eventually formed the moon. Imagine the violence of that moment. Not a crater, not a scar, a reshaping, a rewriting of the planet's mass and spin. And yet, even after that, Earth continued. That's one of the most haunting parts of planetary history. Catastrophe doesn't always mean ending. Sometimes it's just a chapter turn. Each collision fractured the crust, stirred the interior, and opened paths for gases to escape. Hydrogen, carbon monoxide, nitrogen, and water vapor. Because even in a molten world, water can exist. Not as liquid, but as vapor or as chemically bound hydrogen and oxygen inside minerals. Hidden, protected, waiting. This is where the story gets strangely intimate. We tend to imagine water arriving like a gift, ice falling from the sky and melting into oceans. But much of Earth's earliest water may have arrived in quieter forms. Not as visible water, as hydrated rock. Minerals carrying hydrogen and oxygen in their structures, like tiny locked rooms in a crystal lattice. And deep below the forming crust, pressure and chemistry held on to those ingredients even while the surface boiled. So while the top of the planet looked dry, nothing but fire, some of the raw material water was already tucked away, deep, safe, and patient. And slowly, very slowly, the planet began to cool. Cooling isn't a single event. It's a long negotiation between heat and time. Over tens, then hundreds of millions of years, the magma ocean calmed in places. The first crust thickened, thin and fragile, but real, and that allowed something new to happen. Steam that once rose and vanished into space began to linger. The atmosphere thickened, not breathable, not friendly, but present. It became saturated with water vapor. And eventually, when the surface temperature dropped low enough, that vapor began to condense. Clouds formed for the first time. Not the bright cotton clouds we know, but heavy, dark, endless sheets of condensation. And then, rain. The first rainfall on Earth wasn't a gentle beginning. It was relentless. Imagine water falling onto hot rock. The sound wouldn't be soft. It would be constant hissing and roaring, rain striking magma, flashing instantly into steam, and falling again in cycles, like the planet couldn't decide whether to keep the water or throw it back. At first, water couldn't stay. Pools would boil away as soon as they formed. Rivers couldn't carve because land wasn't stable enough to hold a channel. But as cooling continued, something shifted. The crust held longer. The surface stopped remelting everywhere all at once. And water began to accumulate. Puddles became lakes. Lakes became seas. Basins, low places in the newborn crust, began to fill. And the first oceans formed not in a grand cinematic sweep, but gradually, stubbornly, as the planet learned to be cool enough to cradle liquid. This era has a name, the Hadean Eon, named after Hades, the underworld. And honestly, it fits. It was an earth of fire and impact, a world that looked like it belonged to the dark. And yet, it's possible that liquid water existed surprisingly early. That's one of the big shifts in modern thinking. For a long time, scientists imagined the Hadean as a long stretch of molten chaos. No stable surface water for hundreds of millions of years. But evidence, tiny, stubborn evidence, has suggested a quieter truth. Not calm, but cooler than we assumed. Wet earlier than expected. And to really appreciate that, we have to talk about something we rarely think about when we look at the sea, Earth's interior. Because if you only tell the water story from the surface, you miss the deep plot twist. Beneath your feet, far below the crust, lies a mantle. Solid rock, but hot enough to flow over time, like slow-moving wax. The mantle isn't just a layer. It's Earth's engine room, its memory vault. And astonishingly, the mantle may hold as much water as, maybe even more than, all the oceans combined. Not in underground rivers, not in caverns, in minerals, in crystals like ringwoodite and wadzite, which can trap water inside their structures under immense pressure. This is not the kind of water you can scoop up. It doesn't drip. It doesn't slosh. But it's real. It's hydrogen and oxygen bound in ways that only exist deep inside planets. And it matters because it suggests something huge. Earth didn't just get water sprinkled onto it like an afterthought. It may have grown up wet from the inside out. Some of that water arrived early and sank deep. Some was incorporated during accretion, while Earth was still assembling itself. And some of it stayed trapped in the mantle, surviving the planet's hottest eras, waiting for the right conditions to return. That changes the feeling of the story, doesn't it? Instead of a dry Earth later, rescued by comets, we get an Earth with water in its bones. Water as a foundational ingredient, present during the planet's differentiation, when heavy elements sank to form the core and lighter silicates formed the mantle. Water present during the moon forming impact. Water present while the earliest crust cracked and cooled. Water not as a guest, but as family. Now, once the oceans began to form, they weren't like today's oceans. The skies above them weren't blue. There was no free oxygen. The atmosphere was a murky blend. Carbon dioxide, methane, ammonia, water vapor, and other gases that would feel alien to modern lungs. Sunlight hit the surface harshly. No ozone layer meant ultraviolet radiation poured down easily. And yet, the oceans endured, held in place by something delicate and rare, Earth's balance, a little closer to the sun, and water might not have condensed at all, a little farther, and it might have frozen for good. But Earth sat in that golden region, what we now call the habitable zone, where liquid water could exist, not guaranteed, not automatic, but possible. And once possible, it became powerful. The early oceans were likely warm, possibly acidic and rich with dissolved iron. They were stirred constantly by volcanism and impacts. The seafloor was alive with geothermal activity, hydrothermal vents, underwater geysers, spewed heat and minerals into the water, building strange chemical gradients. And in those gradients, something else may have begun. Not fish, not plants, not anything you'd recognize. Just chemistry starting to behave differently because water is not only a substance, it's an environment, a medium where molecules can move, collide, react, recombine. If life was ever going to ignite, water made an excellent cradle. And while that story, life's origin, is its own deep ocean of mystery, what matters tonight is this. Before Earth became a home, before it became green and loud and full of birds, it became wet, a planet of storms, seas, and silence. And in that silence, water didn't just exist. It reshaped everything that came after. Now, to truly chase the water source, we have to follow a trail written not in oceans, but in isotopes, those tiny variations in atoms that act like signatures across time. It begins with hydrogen. Hydrogen is the most abundant element in the universe. Light, ancient, forged in the earliest moments after the Big Bang. But hydrogen isn't uniform. Some hydrogen atoms carry an extra neutron, becoming deuterium, still hydrogen, but heavier. The balance between regular hydrogen and deuterium becomes a kind of cosmic stamp. It hints at where water formed: the cold outer regions, the warmer inner regions, the interstellar medium, the early solar disk. So when scientists measure the DH ratio in Earth seawater, then compare it to comets, meteorites, mantle samples, they're building a map of origins. And when they did that, one thing became clear: comets were not the perfect match we wanted them to be. Many famous comets, like Halley or Hale-Bopp, have DH ratios significantly higher than Earth's oceans. If comets had delivered most of our water, the ocean's chemistry would look different. It doesn't. Some comets have ratios closer, yes, especially some Jupiter family comets. But as a whole, comets are inconsistent, and there's also the question of quantity. Even if comets contributed, they likely couldn't have delivered enough to fill the oceans alone. Which brings us back to the meteorites, those carbonaceous chondrites. They're among the oldest solid objects in the solar system. Little time capsules from the early nebula. Many contain hydrated minerals, evidence that water was locked into their structures from the beginning. And when scientists measured their DH ratios, the match to Earth's oceans was stunning. Not just close, almost perfect, which suggests a quieter, steadier origin story. Earth inherited much of its water through the same process that built the planet, not through a few dramatic icy impacts, but through countless small deliveries of wet rock, over millions of years, like dusk gathering into destiny. The process likely began during accretion. Earth gobbled up everything in its path: dry material, wet material, metal, silicates. The wet bits didn't arrive as oceans. They arrived as chemical potential, water-bound in minerals, carried deep into the mantle, then gradually released through volcanism. Earth didn't just receive water. It processed it. It stored it. It breathed it out. And eventually it rained. And it rained. And it rained. Not a single storm. An era of deluge. Clouds endlessly forming. Water pounding the surface like a kind of planetary baptism. Pools merging into seas. Basins filling. The first coastlines forming in a world still raw. And yet, there's another possibility, one even older. Some scientists believe Earth's water began arriving even earlier than planetimals, before the planet itself was fully formed. In the frigid outer reaches of the solar nebula, ice is formed on dust grains. Water ice, yes, but also carbon monoxide, methane, ammonia. Those icy grains may have drifted inward over time. They didn't melt right away. They stuck to growing clumps. They became part of planetimals and protoplanets. In that model, Earth's wetness isn't a late addition. It's primordial. The planet didn't become wet. It was born wet, at least in parts. And that could explain something curious: the consistency of water's isotopic signature across Earth. From mantle rocks to surface oceans, from ice caps to underground aquifers, the DH ratio remains remarkably stable. That kind of uniformity suggests a shared source, something foundational, not a patchwork of unrelated deliveries. But that still leaves a big haunting question. Even if water arrived early, how did it stay? Early Earth was hot enough to boil water instantly. Solar wind was strong. Impact were constant. Some researchers think Earth's first oceans may have formed and vanished, and formed again. So why didn't all the water escape? Two reasons matter most. First, Earth is big. Its gravity is strong enough to hold on to heavier molecules like water vapor better than smaller worlds can. Second, Earth developed a protective magnetic shield. Its magnetosphere, generated by the motion of its molten iron core. That shield deflects the solar wind, helping preserve the atmosphere and the water within it. Without that magnetosphere, Earth might have suffered a Mars-like fate, a world that once had water but lost much of it to space. So the miracle isn't only that Earth received water. It's that Earth held on to it long enough for oceans to become permanent features. Water came early. It came often. But most of all, it stayed. And in staying, it changed the planet's entire future. Now, in the next part, we're going to return to Earth as it crosses a threshold when oceans stop being temporary and start becoming a planetary system, and when water begins working not just as a presence, but as a force. Because once Earth became wet, it didn't just get oceans. It got a whole new way to be a planet. Let's come back to Earth now. Not as a molten fireball, not as a newborn crust cracking under endless impacts, but as a world hovering on a threshold. A planet beginning to wear its oceans like a loose-fitting robe. Not perfectly settled, not calm, but unmistakably changed. Something profound was shifting, not in a single dramatic moment, but across millions of years as water moved from a vaporized dream into a permanent planetary feature. And the transformation wasn't subtle, because once water was here, once it could linger, collect, cycle, it started rewriting the planet's behavior, not just at the surface. Deep inside, too, water didn't merely fill basins. It began to steer Earth's chemistry, reshape its crust, and quietly set the stage for life to get ambitious. This is where the mantle re-enters the story, not as a background layer, but as a main character. Because the water cycle you know, the one you picture with clouds and rain and rivers, might be only half the story. There's another cycle beneath your feet, older than the forests, older than animals, possibly as old as the oceans themselves. The deep water cycle. It works like this. Earth's surface isn't one solid shell. It's broken into moving plates. Tectonic plates, sliding over the softer, slowly flowing mantle below. And where plates collide, one can sink under another in a process called subduction. When that happens, the descending plate doesn't just carry rock. It carries water, not as liquid sloshing downward, but as water locked inside minerals. Certain rocks on the seafloor interact with seawater over time, forming hydrated minerals, like serpentine, that hold water within their structure. So when that slab of oceanic crust dives down into the mantle, it drags that bound water with it, down, hundreds of kilom, into crushing pressures and rising temperatures where rocks behave differently, where chemistry becomes a slow, powerful force. As the slab descends, the heat begins to squeeze the water out. Minerals break down. Water is released. And that released water doesn't just sit there. It changes everything around it. Water lowers the melting point of mantle rock. That means that in the presence of water, mantle material can begin to melt more easily, creating magma. And magma rises. Eventually, some of it erupts as volcanoes. Some seeps out along mid-ocean ridges. Some becomes new crust. And along the way, it releases gases back to the surface, carbon dioxide, sulfur, nitrogen, and water vapor. So Earth breathes. Water goes down with sinking plates. Water comes back up through magma and volcanoes. Over geological time, this becomes a planetary heartbeat. Water in, water out. Not fast, not dramatic. Steady and vital. Because this deep cycle may be one of the reasons Earth's oceans reach a stable volume instead of endlessly accumulating or disappearing. It's as if Earth developed a long-term balancing system, storing water in its interior, releasing it back, circulating it through rock. This matters because it suggests something bigger than Earth got water. It suggests Earth learned to manage water. And that management, this slow cycling, might be one of the reasons Earth became the kind of planet where life could persist for billions of years. Now, while all this was happening deep underground, the surface oceans were doing their own quiet work. They were changing the chemistry of the world. They were becoming a laboratory. Rainwater, slightly acidic because it absorbs gases in the air, began to break down rock on the earliest land masses. This process is called weathering. It grinds stone into sediments, dissolves minerals, and carries ions into the sea. Over time, these dissolved minerals accumulate in the ocean. Calcium, magnesium, sodium, potassium, the elemental flavors of seawater that still define it today. And at the same time, something else happened that would change Earth's climate. Weathering draws carbon dioxide out of the atmosphere. CO2 dissolves in rainwater, reacts with rocks, and eventually gets locked away in carbonate minerals. Those minerals can end up as sediments, then rock layers, then even be dragged down by subduction and returned again by volcanoes. This is the beginning of Earth's long carbon cycle, a planetary thermostat, because carbon dioxide is a greenhouse gas. It traps heat. If there's too much CO2, Earth warms. If there's too little, Earth cools, and water, through weathering, erosion, and ocean chemistry, helped regulate how much CO2 lingered in the sky. It's strange, isn't it? You might think of water as something gentle, soothing, quiet. But here, water is controlling the climate. Water is moderating the temperature. Water is shaping Earth's long-term habitability, like a hand resting on a dial. And while the oceans were absorbing minerals and balancing carbon, they were also hosting something that would eventually alter the atmosphere itself. Life. Not the kind of life you imagine when you think of beaches and whales. The earliest signs of life on Earth appear around 3.8 billion years ago, maybe even earlier depending on interpretation. At first it was microbial. Small, simple, astonishing. These early organisms didn't breathe oxygen. In fact, oxygen would have been poisonous to many of them. They lived off chemistry, using energy from hydrothermal vents or sunlight filtered through a hazy sky. And among these early life forms were cyanobacteria, tiny architects of planetary change. Cyanobacteria lived in shallow waters, forming mats and layered domes called stromatolites. They were small, but they had a talent that would rewrite the planet. They performed photosynthesis. They used sunlight to turn carbon dioxide and water into energy and released oxygen as a waste product. At first, that oxygen didn't accumulate in the air. Earth's oceans were full of dissolved iron, and oxygen reacts eagerly with iron. So the oxygen would bind with iron and form iron oxides, rust, sinking to the seafloor. Over time, this created the banded iron formations that geologists still study and mine today. Striped layers of ancient rust, a fossil record of the planet slowly oxygenating. But eventually, the ocean's iron became saturated, and oxygen began to linger, first in water, then in the atmosphere. This transition, the Great Oxidation Event around 2.4 billion years ago, was not a sudden flip. It was slow and uneven, but it reshaped Earth's chemistry forever. Oxygen is reactive. It breaks bonds. It enables a far more efficient way for organisms to extract energy from food. And for life, that efficiency mattered, because aerobic respiration, using oxygen, unlocks far more energy than anaerobic methods. That extra energy allowed cells to grow larger, more complex, more capable. It laid the groundwork for eukaryotic cells with nuclei and internal organelles, and eventually, much later, for multicellular life. But in the beginning, oxygen was a crisis. It was toxic. It likely wiped out many anaerobic communities. Extinction by oxidation. And yet, it also opened the door to new kind of life, new pathways, new complexity. And again, notice how deeply water is involved. Without oceans, cyanobacteria wouldn't have had such a vast, stable home. Without water, oxygen couldn't dissolve and spread and react in the same way. Water wasn't just the setting for this transformation. Water was the medium through which it happened. Meanwhile, water kept reshaping the planet's surface. Rivers began to carve. Sediments began to build. Oceans began to circulate. Glaciers formed in colder regions and ground rock into dust. Rain sculpted valleys. Streams braided across the land. Deltas formed, rich in nutrients. The hydrological cycle, evaporation, condensation, precipitation, became one of Earth's major engines. Powered by sunlight, it redistributed heat across the globe. It carried moisture to continents. It shaped climate zones. And once that cycle became stable, Earth became not just wet, but habitable in a deeper sense. Not only survivable, but capable of supporting ecosystems that could spread, diversify, and endure. And there's another subtle element here: pH. Early oceans were likely more acidic than modern oceans because of high levels of dissolved CO2 and other gases. Over time, weathering of silicate rocks helped neutralize that acidity, pushing oceans toward a more balanced pH, a range more favorable for many forms of chemistry, and later, life. Again, water dissolves. Water carries. Water buffers. Water acts as the planet's chemical mediator. And then there's salt. Why is seawater salty? Because water is an eroder. Rainwater breaks rock down and picks up ions, sodium, chloride, calcium, sulfate, and carries them to the sea. Some are used by organisms. Some precipitate out as minerals. Many remain dissolved, accumulating over eons. So in a way, the ocean is a kind of memory pool, a record of Earth's erosion, a basin holding the dissolved history of continents. And that dissolved chemistry matters. Salinity influences density and circulation. Minerals influence nutrient availability. Temperature affects solubility. Every property shapes what can live there and how. Life didn't just evolve in generic water. It evolved in earth water, a specific blend of temperature, salinity, minerals, and chemistry unique to this planet's long history. And at this point in the story, we're no longer talking about water as a thing Earth has. We're talking about water as Earth's rhythm. Water creates clouds. Clouds scatter sunlight. Scattered sunlight cools the surface. Rain falls. Rivers flow. Sediments bury carbon. Subduction drags water and carbon back down. Volcanoes release them again. It's not a straight chain. It's a spiral. A loop dance between rock, air, water, and time. And water is the tempo. Now, one of the most profound gifts water gave Earth was moderation. Water resists temperature change. It warms slowly and cools slowly. It stores heat and moves it across great distances. That thermal inertia helped Earth avoid wild swings that might have sterilized the surface repeatedly. And this brings us to a famous puzzle, the faint young sun paradox. Early in the sun's history, it was fainter, only about 70% as bright as today. If you follow simple logic, early Earth should have been frozen, and yet evidence suggests liquid water existed as early as 4.3 to 4.4 billion years ago. So how? The answer likely involves greenhouse gases, carbon dioxide, methane, water vapor, released by volcanic activity. These gases trapped heat, keeping the planet warm enough for liquid oceans despite a dimmer sun. But the balance was delicate. Too much greenhouse gas, and Earth could have become like Venus. Too little, and it could have frozen like Mars. Water helped regulate that balance through weathering and the carbon cycle. So water wasn't just participating in climate. It was stabilizing it, but that stabilization wasn't perfect. Sometimes Earth tipped. Sometimes the feedback loops overshot. There were eras when water didn't just buffer climate. It amplified extremes. One dramatic example is the snowball Earth events. Deep freezes around 700 million years ago. In these episodes, glaciers may have extended nearly to the equator. The planet may have become a gleaming white sphere. Ice reflects sunlight. This is the albedo effect. More ice means more reflection, which means less heat absorbed, which means more cooling, which means more ice. A runaway freeze. But even then, volcanism continued. See O2 build up slowly in the atmosphere because weathering and ocean absorption were limited under ice. Eventually, greenhouse warming became strong enough to melt the ice, possibly triggering rapid, catastrophic thawing, floods, intense weathering, a rebound of life, water as threat and salvation. And patterns like this show up again and again in Earth's history. Catastrophe followed by recovery, breakdown followed by new complexity. Water conducts that rhythm. It freezes, it melts, it dissolves, it circulates, it stores heat, it carries nutrients. It's the medium through which Earth changes. And here's a bigger truth to hold gently. Water didn't just transform Earth. It differentiated Earth. Because of water, Earth became the only planet in our solar system with active plate tectonics, long-term climate regulation, stable oceans, and life that could persist and evolve over billions of years. Other planets had water briefly. Mars had rivers and lakes and maybe seas, but it lost much of its atmosphere and protection. Venus may have had oceans, but it ran into a runaway greenhouse fate. Only Earth held on. Only Earth cycled water deep and slow. Only Earth turned water into a self-sustaining system. And that's why when we search for life elsewhere, on distant exoplanets around distant stars, the first question is often about water, not as a guarantee, as a hint, because water isn't just a solvent. It's a sign that a planet might be able to balance chaos with calm, that it might sustain change without losing itself, that it might carry chemistry far enough to become biology. And as we drift toward the next part, we're going to zoom out even further, beyond Earth, beyond the solar system, because as personal as our oceans feel, Their story may begin in the dark between stars. And once you realize that, a glass of water becomes something else entirely. If you zoom out far enough, the oceans stop looking like Earth's feature and start looking like the universe's habit. Because here's a truth that sounds like poetry but lands like science. The water you drink is older than the sun, not metaphorically, literally. Your water is a mixture of ancient elements, hydrogen and oxygen, that were forged in different epochs of the cosmos. Hydrogen is so old it predates stars entirely. Oxygen is younger, born later in the hearts of stars that lived and died before our solar system existed. And somewhere along the way, out in the cold, dark places where light is thin and time is slow, hydrogen met oxygen, and water began to form. Let's start with hydrogen, because it's the beginning of so many beginnings. Hydrogen emerged in the first few minutes after the Big Bang, when the universe cooled just enough for protons and neutrons to settle into stable combinations. Back then, the cosmos was mostly hydrogen and helium, simple, light, newborn. Oxygen wasn't around yet, not for a long time. Oxygen had to be made later, inside stars. In the deep furnaces of stellar cores, lighter elements fuse into heavier ones. Over millions of billions of years, stars build up a layered chemistry. Hydrogen to helium, helium to carbon, carbon to oxygen, and onward. And when massive stars die, they don't go gently. They explode. Supernovae, scattering the elements they forge into the galaxy like seeds flung into dark soil. That means oxygen, one half of the water molecule, was born in dying stars. So already, water has this dual ancestry. Hydrogen from the universe's first breath, oxygen from stellar death. And then there's the question of when those ingredients actually turned into water. We know water exists in interstellar space, not as oceans, of course, but as vapor and ice, frost on dust grains drifting through molecular clouds. Some of the oldest water ever detected appears in cold interstellar regions that are over 12 billion years old. Imagine that, water molecules forming and freezing onto dust grains long before our sun existed, long before Earth. Long before there were planets at all in this particular corner of the galaxy. Just water, stuck to dust, drifting in darkness for eons. Now, when the solar system began to form, it formed from one of these clouds, a collapsing nebula of gas and dust. The cloud flattened into a rotating disk. The protoplanetary disk, the raw material of planets. And embedded in that disk were grains of dust, some already coated in ancient ice. Not all of it, but some, which leads to a fascinating possibility. A portion of Earth's water might be inherited, water that existed before the solar system was born, surviving the violent transition from cloud to disk to planet. Some scientists have suggested that a significant fraction of Earth's water could be primordial in that sense, carried into the solar system as interstellar ice, then incorporated into growing planetimals, then into Earth. So when you hold a glass of water, you might be holding a few molecules that have been water continuously since before the sun was even a twinkle in the cosmic neighborhood. Now, water in the solar disk wasn't evenly distributed. Close to the forming sun, it was too hot for ice to survive. Water existed there mostly as vapor and rock and metal dominated. Farther out, beyond a boundary called the snow line, temperatures dropped low enough for water to freeze. In those colder regions, ice was abundant. Dust grains were frosted. Planetimals formed with water locked in their structures. The snow line matters because it shapes what kind of planets form where. Inside it, you get rocky worlds, Mercury, Venus, Earth, Mars. Beyond it, you get gas giants and icy bodies, Jupiter, Saturn, Uranus, Neptune, plus the comets and Kuiper Belt objects. But here's the catch. The solar system didn't form in tidy rows like a museum display. It formed in motion. Dust moved. Rocks migrated. Planets shifted. Gravity nudged. Turbulence stirred. So material didn't stay neatly on its side of the snow line. Water-rich bodies from farther out could be scattered inward. Dry bodies from closer and could be flung outward. And this mixing, radial mixing, may be one of the reasons Earth ended up with so much water despite forming in a region that should have been relatively dry. It's like building a house near a desert, but your supply trucks keep bringing in wet clay from a faraway valley. You didn't make the water here, but you got deliveries. And some deliveries may have been happening before Earth was even fully built. Which brings us to a bigger point. Earth isn't the only world touched by water. Water seems to show up all over the solar system, like it's a recurring theme. Mars, for instance, wears the scars of rivers and lakes. We see dried channels and ancient deltas carved into its surface. Rovers have found clays and minerals that only form in the presence of water. There may still be briny reservoirs underground, and we know there's ice at the poles and in subsurface deposits. Mars wasn't always dry. It lost much of its water over time, likely because it's smaller and its magnetic field weakened. Without strong protection, solar wind stripped away much of its atmosphere, and water became harder to keep stable on the surface. Then there's Venus. Venus is Earth's near twin in size, but it's a nightmare world. Crushing atmospheric pressure, searing temperatures, thick carbon dioxide, sulfuric acid clouds. Some models suggest Venus might once have had oceans, but being close to the sun, Venus was more vulnerable to runaway greenhouse warming. Water would have evaporated, filling the atmosphere as vapor. Ultraviolet light would split water molecules. Hydrogen would escape into space. Oxygen would react with rocks or be lost. And once that happened, Venus would dry out permanently. So Venus may have had water, but it couldn't hold on to it. Earth could. Now, if we travel outward, water shows up again, sometimes in places where you wouldn't expect it. Look at Jupiter's moon Europa. From the outside, it looks like a smooth shell of ice with cracks like veins. But beneath that ice, most scientists believe Europa holds a deep subsurface ocean, kept warm not by sunlight, but by tidal forces. Jupiter's gravity squeezes Europa as it orbits, generating heat, keeping water liquid under the ice. Ganymede and Callisto may also hide oceans. Saturn's tiny moon Enceladus is even more dramatic. It shoots geysers of water into space, plumes of salty vapor and ice grains erupting from fractures near its south pole. Those plumes contain water, salts, and organic compounds, ingredients that make scientists lean closer to the data with quiet excitement. And then there's Titan. Titan has lakes and rivers, but not of water, of methane and ethane. It's so cold that water ice behaves like rock, and methane behaves like water. Titan runs a kind of mirror hydrological cycle in hydrocarbons, with clouds, rain, rivers, and seas, just made of different molecules. All of this tells us something eerie and beautiful. Water isn't rare in the universe. Liquid water might be rarer, because it needs the right temperature and pressure, but water itself, as ice or vapor, seems to be everywhere dust and cold can meet. Now, beyond the solar system, we've found water in protoplanetary disks around other stars. We detected water vapor in the atmospheres of exoplanets. Some worlds may be ocean planets covered entirely in water, with no land at all. Others may be ice-covered or desert dry. We don't yet know how common Earth-like ocean worlds really are, but we keep looking. Because if Earth's story teaches us anything, it's that water doesn't just decorate a planet. It changes what the planet can become. Water dissolves and transports chemicals. It buffers temperature. It enables complex chemistry. It shapes geology. And on Earth, it became the stage where life could try out its first fragile experiments. Which brings us to a quiet, strange intimacy. Even if water is common out there, the water on Earth is personal, because all the water here is part of one continuous system. It evaporates. It condenses. It falls. It freezes. It melts. It flows. But it almost never truly leaves. That means the water inside you right now, the water in your blood, your breath, your cells, may have once been in a dinosaur's footprint, or inside the sap of an ancient fern, or part of a glacier during the last ice age, or swirling in an ocean current when the continents were arranged in a completely different shape. Water connects moments. It connects beings. It is a shared inheritance across time. And if you follow that inheritance backward far enough, you end up in space, in cold clouds, on dust grains, in meteorites, in the invisible chemistry of the early solar disk. So when we ask, where did Earth's water come from? We're asking a science question, yes, but it's also a cosmic question. We're asking how the universe learns to hold warmth, how stardust becomes rivers, how chaos gives rise to calm, how a planet learns to sing a soft, liquid song in the dark. And now, as we drift into the next part, we'll come back closer to home, back into the human side of the mystery. Because as ancient as water is, our understanding of it is surprisingly recent. And the story of how we discovered where Earth's water came from is filled with patient minds, tiny crystals, and instruments delicate enough to hear the whisper of a single atom. In other words, the ocean began with a question, and the next part is about the people who listened. Some mysteries don't get solved with a single dramatic discovery. They get solved the way coastlines form, slowly over time, through countless small movements that add up to something undeniable. That's what the water story feels like in science. Not one hero, not one eureka moment, but a long, quiet convergence. Chemistry meeting geology, lab work meeting space missions, ancient crystals meeting modern instruments. And for a long time, the question sounded almost mythic. Where did Earth's water come from? But scientists treated it with the patience of people who understand that the planet keeps records if you learn how to read them. Let's begin with something small enough to fit on your fingertip, yet old enough to outlast mountains. Zircons. Zircons are tiny crystals that can survive intense heat and pressure. They're like stubborn little time capsules, holding on to chemical information long after the rocks around them have been melted, crushed, and remade. In the early 2000s, a geochemist named John Valley at the University of Wisconsin, Madison studied zircons from the Jack Hills in Western Australia, some of the oldest known minerals on Earth. These crystals were about 4.4 billion years old. That number is hard to hold in your mind. Earth itself formed around 4.54 billion years ago, so these zircons formed astonishingly early, almost right after the planet's birth. And inside them, Valley found something subtle but powerful: oxygen isotopic signatures, suggesting interaction with liquid water, not just water vapor, not just a wet interior, actual surface water, water interacting with crust. If that interpretation is correct, it implies that Earth may have had stable crust and possibly oceans within about 100 million years of forming. That was shocking, because for decades, the standard picture painted a Haitian Earth as a long-lasting hellscape, molten, chaotic, and dry for far longer. But those zircons hinted at something gentler beneath the violence. Not peaceful, certainly, but wet sooner than expected. Valley didn't claim to have found the first drop of water, but he helped push the timeline back. He made scientists rethink when oceans might have appeared, and how quickly a planet can cool enough to hold them. That was one piece of the puzzle. Timing. But another piece was origin. And this is where the isotopic fingerprints become the main language of the story. Around that same era, researchers began comparing the DH ratio, deuterium to hydrogen, in different solar system materials. The logic was simple and elegant. If you can match Earth's water isotopic signature to a known source, you get a clue about where it came from. One of the scientists deeply involved in this line of work was Alexander Halliday and his team at Oxford. They focused on meteorites, especially carbonaceous chondrites, those ancient water-rich space rocks that formed early and preserved primitive chemistry. And when they compared hydrogen isotopes, they found something that kept showing up across studies. The hydrogen in carbonaceous chondrites matched Earth's oceans more closely than most comets did. It was a quiet revolution, because for decades, comets were the romantic suspects. Bright, icy visitors from the outer dark. It was easy to imagine them slamming into a dry Earth and leaving behind oceans. It made intuitive sense. But chemistry doesn't care what feels intuitive. Many comets, especially those from the distant outer reservoirs, carry too much deuterium. Their DH ratios often sit noticeably above Earth's ocean value. If Earth's oceans had come mostly from those comets, our seawater would be isotopically different. It isn't. That doesn't mean comets contributed nothing. It just suggests they weren't the main supplier. So the attention shifted from icy drama to rocky consistency, from comets to wet asteroids and meteorites. Now, while researchers like Halliday were tightening the chemical case for carbonaceous chondrites, another line of evidence was developing deeper inside Earth. Because if Earth's water came from the building blocks of the planet, then Earth's interior should also carry clues. This is where the work of teams studying mantle-derived rocks becomes so important. Remember those tiny glass inclusions trapped inside olivine? That kind of material is priceless because it can preserve volatile chemistry, like water and hydrogen, without being overprinted by surface processes. And that brings us back to Dr. Lydia Halleys and her team, studying mantle samples brought up by volcanic eruptions. Their measurements suggested hydrogen isotopic ratios in some mantle reservoirs were lower than the oceans, lower even than carbonaceous chondrites in some cases, which raised an unsettling question. Could some of Earth's hydrogen have come from an even more primitive source, not delivered as water by asteroids, but captured from the solar nebula itself? This is one of the more debated and fascinating possibilities. The solar nebula, the disk of gas surrounding the newborn sun, was rich in hydrogen. If the young Earth captured some of that hydrogen gas early on, and later it reacted with oxygen-bearing minerals, it could have formed water inside Earth. In that scenario, part of Earth's water story isn't about delivery, it's about retention. Earth might have held on to some nebular hydrogen during formation, then converted it into water over time. Not every scientist agrees on how large that contribution could be, and the debate remains active. But that's the beauty of planetary science. Even the answer is often a blend, a spectrum of contributions rather than a single source. And the debate didn't stay on Earth. It went to space. Because when you want to test a comet theory, you don't just speculate, you go measure a comet. That's what missions like ESA's Rosetta did. Rosetta studied Comet 67P/Churyumov, Gerasimenko in detail, and when it measured the comet's DH ratio, it found a value around 3 times higher than Earth's oceans. That result didn't completely kill the comet idea, but it made it much harder to defend comets as the primary source. Again, comets could be contributors, but a major mismatch in isotopic signature is a serious problem if you're trying to explain most of Earth's water. And yet, just when it seemed like comets were being pushed aside, science did what science always does. It complicated the story. Because some comets, especially certain Jupiter family comets, have DH ratios closer to Earth's. Not all comets are the same. Their isotopic signatures vary depending on where and how they formed. So the comet story becomes less like comets did it or comets didn't do it, and more like comets are a mixed population. Some look like poor matches, some look closer, but overall, the best consistent match across multiple studies keeps pointing to carbonaceous chondrites and water-rich asteroids. And here's where modern sample return missions enter like careful messengers. Because for decades, we studied meteorites that fell to Earth. Valuable, yes, but altered by atmospheric entry and weathering. The dream was always, what if we could bring back pristine samples directly from asteroids? Japan's Hayabusa 2 brought back samples from asteroid Ryugu in 2020. NASA's OSIRIS-RX returned samples from asteroid Bennu in 2023. And those samples matter because they come from carbon-rich bodies suspected to contain hydrated minerals and organic compounds. Exactly the kind of material that could have helped seed Earth with water and the chemical building blocks of life. Early analyses reported clay-like minerals and evidence of aqueous alteration, signs that water interacted with these rocks early in solar system history. The story keeps repeating. Wet rock, hydrated minerals, isotopic fingerprints that echo Earth. So the water question isn't being answered by one field alone. It's a chorus. Astrophysicists model how material moves in protoplanetary disks. Cosmochemists analyze meteorites atom by atom. Geologists study ancient minerals like zircons. Planetary scientists send spacecraft to measure comets. Engineers build machines that can scoop dust from an asteroid millions of kilometers away. And all of it comes together around a simple truth. Earth's water story is not a single delivery truck. It's a supply chain. A long and messy chain spanning interstellar space. The solar nebula, asteroid belts, planetary accretion, deep mantle storage, volcanic outgassing, rainfall, oceans, and continual cycling. Which means the question becomes less like, where did water come from? And more like, how did Earth become the kind of place where water could stay? Because even if you deliver water, it doesn't matter unless the planet can keep it. Earth did, through gravity, through the magnetosphere, through deep storage, through cycling, through sheer persistence. And behind every one of these insights, there's another quiet story that matters too, the human story, because this isn't fast work. A single isotope measurement can take years to validate. A hypothesis can wait decades for better instruments. Some meteorites collected in the 1960s are still revealing new secrets today, because modern tools can see things older tools couldn't. Science here isn't a sprint. It's a pilgrimage, a slow walk through time, guided by data, and the tools. Oh, the tools are delicate in a way that feels almost surreal. Researchers use instruments like SIMS, secondary ion mass spectrometers, to measure isotopic ratios in tiny spots of a mineral. They can distinguish between water trapped inside a crystal structure and water that seeped in later. They can read the signature of hydrogen atoms trapped in glass, inclusions smaller than a grain of sand. It's like trying to hear a whisper in a hurricane and still getting the words. And these words, these ratios, these peaks on graphs, are how we translate the ancient language of atoms into something human minds can hold. A story about water, yes, but also about patience, about curiosity, about our ability to look at a pebble that fell from the sky and realize it might be carrying the memory of an ocean. And in the next part, we'll drift deeper into that translation process. We'll talk about how scientists interrogate atoms, how deep Earth discoveries change the story again, and how even the moon, long assumed bone dry, ended up whispering clues about water's earliest days. Because sometimes the best way to understand Earth is to listen to the worlds around it. There's something almost tender about the way scientists study water's origin. Not because the work is sentimental. It's not. It's precise, stubborn, technical. It's ratios and instruments and calibration curves. But because the act itself is quiet. It's people leaning close to tiny things, dust grains, crystal inclusions, microscopic defects inside minerals, trying to hear a story that's been whispering for billions of years. And the strange truth is, we don't read the history of Earth's water by staring at oceans. We read it by listening to atoms. That might be the most surprising part of all, because the evidence isn't mostly out there rolling in waves. A lot of it is hidden inside rock, inside diamonds, inside lunar glass, inside ancient meteorites that look like ordinary stones until you remember they've traveled through space. Let's start with the lab tools, because they're almost magical in their delicacy. One of the workhorses of this research is something called a secondary ion mass spectrometer, often shortened to SIMS. The basic idea is simple. You bombard a tiny area of a sample with ions, which knocks atoms loose. Those atoms become a spray, and the instrument measures them by mass and charge. But simple here doesn't mean easy, because SIMS isn't measuring boulders. It's measuring pinpricks, spots so small they can fit inside a single mineral grain. It can tell you the isotopic ratios in a tiny pocket of glass sealed inside olivine, exactly the kind of inclusion that carries deep mantle information. And in water origin science, that's everything. Because the difference between water locked inside a crystal during formation and water that seeped in later can completely change the story. So scientists build methods to isolate original signals. They look for pristine inclusions. They compare multiple isotopes. They check for contamination. They repeat measurements. They argue over interpretations, then argue again when better instruments arrive. This is how planetary history gets built. Not through a single perfect measurement, but through a slow tightening of uncertainty. And one of the biggest places uncertainty used to hide was the deep Earth itself. For a long time, many people pictured Earth's interior as mostly dry rock. Hot, yes. Active, yes, but not carrying much water. But then, evidence began to shift the view. Laboratory experiments showed that certain mantle minerals, especially those found in the mantle transition zone, can store surprising amounts of water, not as liquid, as structurally bound hydroxyl groups inside crystal lattices. Two famous examples are wadsleyite and ringwoodite, minerals that exist only at high pressures, hundreds of kiloohm beneath the surface. Researchers discovered these minerals can hold up to around 1% water by weight, sometimes more under certain conditions. That doesn't sound like much until you scale it up. The mantle transition zone is enormous, and if even a fraction of it contains water-bearing minerals, the total stored water could rival the volume of Earth's surface oceans. This idea used to feel theoretical, interesting, plausible, but hard to prove. Then came a moment that felt like a single drop changing the sound of an entire room. In 2014, a team led by Graham Pearson reported something extraordinary, a natural sample of ringwoodite trapped inside a diamond from Brazil. A diamond is like a vault. It forms deep underground and can trap inclusions, tiny pieces of surrounding environment, then carry them upward as the diamond is brought closer to the surface. So Pearson's team found ringwoodite inside that diamond, and the ringwoodite contained water. Again, not water you could pour out, but water bound in the mineral structure, confirmed through careful analysis. It was the first direct evidence that the mantle transition zone isn't dry. It was like finding dew in a cave and realizing the whole cavern may be wet. And suddenly, Earth's water story expanded downward. The oceans were no longer the main reservoir by default. They became the visible surface expression of a deeper, more complex water system, a planet that stores water inside itself and cycles it over geological time. Now, if that deep water exists, it raises a beautiful and unsettling implication. Some of Earth's water didn't just arrive and sit on the surface. It was incorporated early, stored deep, and has been cycling ever since. Which brings us to a different world entirely. The moon. For much of modern history, the moon was treated as dry and dead, dusty, barren, and lacking volatiles. But in the 2000s, that assumption began to unravel. NASA's Moon Mineralogy Mapper, flown on India's Chandrayaan-1 mission, detected spectral signatures consistent with hydroxyl on the lunar surface. OH groups that hint at water-related chemistry. Follow-up studies supported the presence of water ice in permanently shadowed craters near the lunar poles, places so cold that sunlight never reaches them, and ice can persist for billions of years. That's already surprising. But the bigger surprise came from the moon's volcanic past. Some lunar volcanic glass beads, samples brought back by Apollo astronauts, were found decades later to contain measurable amounts of water. These beads formed from magma, meaning the water wasn't a surface deposit. It was tied to the moon's interior processes. And that is where the story gets deliciously complicated. If the prevailing model is correct, that the moon formed largely from debris after the Theia impact, then the moon's interior is linked to Earth's mantle. So if the moon had water in its interior early on, that suggests Earth's mantle had water too. Not later. Early. During the era of violent formation, which supports the idea that Earth's water wasn't simply a late delivery from comets, but something deeply woven into Earth's building phase. Again, not everyone agrees on precise amounts or timing, but the direction of evidence keeps leaning toward a wet interior from early on. Now, if we step back, what's striking is how interdisciplinary this hunt really is. This isn't one field solving one problem. It's astrophysics meeting geochemistry meeting geophysics meeting planetary science meeting engineering. Astrophysicists model how protoplanetary disks evolve, how dust clumps, how the snow line moves, how planets migrate. Geochemists measure isotopes in rocks and inclusions. Geophysicists simulate deep Earth pressures and mineral behavior. Planetary scientists interpret crater records and orbital dynamics. Engineers build spacecraft that can survive launch, navigate for years, and return tiny samples intact. And each discipline brings a different angle to the same question. Now, let's talk about one of the more dramatic angles. Sample return missions. We mentioned Hayabusa 2 and OSIRIS-RX earlier, but it's worth sitting with what these missions represent. For centuries, we relied mostly on meteorites that land on Earth. They're valuable, absolutely, but they come with uncertainty. They pass through the atmosphere, heat up, fracture, weather, and in many cases sit on Earth's surface exposed to water and air. Sample return missions bring something different. Pristine material, collected directly from a known asteroid, kept as uncontaminated as possible, delivered into the hands of labs around the world. Japan's Hayabusa 2 returned samples from asteroid Ryugu in 2020. NASA's OSIRIS-RX returned samples from asteroid Bennu in 2023. And both Ryugu and Bennu are carbon-rich bodies suspected to contain hydrated minerals and organic chemistry. In other words, Exactly the kind of material that could have helped seed the inner solar system with water and the ingredients of life. And early analyses of these returned samples have supported that suspicion, finding clays, hydrated minerals, and organic compounds. Each of these findings is like another breadcrumb, leading back to the same trail: water-rich asteroids, hydrated minerals, a chemical match with Earth's ocean water. Now, none of this means Earth's water has a single neat origin. That's a misconception people often want. A clean answer with one source and one delivery moment. But the Rayall story appears to be more layered. Earth's water likely came from a combination: water inherited from early solar system material, possibly including interstellar ice, water delivered by carbonaceous, water-rich planetimals and asteroids, possibly a contribution from captured solar nebula hydrogen converted later into water, a smaller, inconsistent contribution from comets. And then once it was here, Earth's interior processes did what Earth does best. It recycled, it stored, it released, it kept water in play. And here, there's a quiet philosophical shift, because the mystery becomes less about where did it come from and more about how did it become stable. Plenty of places may receive water, but keeping it long-term, holding on to it through bombardment, through heating, through atmospheric loss, that's a harder feat. Earth did it. Mars did not. Venus did not. The moon has water, but not oceans. Earth uniquely built a stable water system with deep cycling and surface persistence. And that's why deep water discoveries matter so much. They suggest Earth isn't just a wet surface over dry rock. It's a wet planet through and through. Water on top, water below, water cycling between layers. A planet that stores oceans inside minerals like secrets. Now, in the next part, we'll dive even deeper into the language that makes all this possible: isotopes. Because isotopes aren't just numbers on graphs. They're the way we link ocean water to meteorites, to comets, to deep mantle reservoirs, to ancient cosmic clouds. They're the fingerprints water carries across time. And once you learn how those fingerprints work, you start seeing water differently. Not as something here, but as something with a passport, a traveler, a witness, a quiet storyteller that never forgot where it came from. If water could speak, it wouldn't tell its story in sentences. It would tell in ratios, in tiny differences, so subtle you'd miss them unless you had the right tools and the patience to listen, because water, like everything made of atoms, carries history in its structure, not as memory in a mystical sense, but as a physical signature, a record of where it formed, what it went through, and how long it has been traveling, and that record is written in isotopes. So tonight, let's slow down and settle into that word for a moment. An isotope is a version of an element that has the same number of protons but a different number of neutrons. Same identity, slightly different weight. Like the same song played in a lower key. Hydrogen, the simplest element, has isotopes too. Most hydrogen atoms have one proton and no neutrons, but a small fraction have one proton and one neutron. That heavier version is deuterium, still hydrogen, but heavier. And because deuterium behaves just slightly differently in chemical reactions, especially in cold conditions, it ends up being more common in some places than others. That's why the DH ratio, deuterium to hydrogen, matters so much. It's one of the most powerful fingerprints in planetary science. It acts like a passport stamp. Water formed in very cold environments tends to have higher deuterium enrichment. That's because in cold conditions, chemical fractionation favors heavier isotopes getting locked into certain molecules more readily. Water formed under warmer conditions tends to have lower deuterium. So when scientists measure the DH ratio in Earth's oceans and compare to other reservoirs, comets, meteorites, the solar nebula, deep mantle samples, they're not just collecting data, they're tracing lineage. And one of the most striking results of all this work is how stable Earth's seawater DH ratio has been. Across ice caps, oceans, and many groundwater reservoirs, the ratio stays remarkably consistent. It fluctuates a little, of course. Local processes can shift it slightly. But overall, Earth's surface water seems to share a common isotopic accent that suggests a shared origin, or at least a strongly mixed reservoir over geological time. Now, when scientists first tried to solve the origin question, comets were the most cinematic suspect. Comets are icy. They come from the cold outskirts. It's easy to imagine them delivering water like frozen cargo ships smashing into early Earth. But when researchers measured the DH ratios of many comets, the results didn't line up cleanly. Some comets, especially those studied early, had DH ratios significantly higher than Earth's oceans. Not just a little higher, but enough to make it hard to argue they were the main source. Then came more comet measurements. More nuance. Some comets had closer ratios, especially certain Jupiter family comets. But overall, comets look like a messy population. Diverse origins, diverse histories, inconsistent matches. They didn't give us a simple answer. Meteorites, on the other hand, started to look like quieter suspects with stronger alibis, particularly carbonaceous chondrites. These are ancient meteorites rich in carbon and hydrated minerals. They formed early in solar system history and often contain water bound within their mineral structure. When scientists measured their hydrogen isotopes, many carbonaceous samples matched Earth's ocean DH ratio surprisingly well. Sometimes, so it felt like the pieces were finally snapping together. It suggested a scenario where Earth's water came largely from the same type of material that helped build the planet, water-bearing asteroids and planetimals, not from a handful of rare dramatic comet impacts, but from billions of steady deliveries during accretion. Now, here's where the story gets even deeper, because it's not just the ocean that has a DH ratio. The mantle does too. And when scientists measure mantle-derived samples, especially protected inclusions, sometimes the mantle shows a different signature, often lower deuterium than the ocean. That doesn't necessarily mean Earth's water came from an entirely different source. It could mean mixing happened in complex ways. It could mean some reservoirs are older and less altered. It could mean different processes fractionated isotopes differently over time. But what it definitely means is this. Earth is not a single bucket of water. Earth is multiple reservoirs exchanging water over long timescales. Surface oceans, ice, groundwater, atmosphere, mantle, and maybe even deeper. And this is why isotopes are so valuable. They allow us to trace how these reservoirs connect and diverge. Now, it isn't just hydrogen isotopes that matter. Oxygen isotopes matter too. Oxygen has multiple isotopes, O16, O17, O18, with different abundances depending on formation conditions. These can tell us about interactions between water and rock, about temperatures of formation, about ancient crust processes. This is why zircons were such a big deal. Their oxygen isotopes hinted at early interactions with liquid water. They suggested that water wasn't just trapped deep inside Earth. It may have been present at the surface very early. So isotopes don't answer a single question. They answer a network of questions. Where did water come from? When did it appear on the surface? How much stayed in the interior? How has it cycled over time? Now, let's shift to an even stranger thought. The DH ratio doesn't just link Earth to meteorites and comets. It links Earth to the cosmic environment beyond the solar system, because the interstellar medium, the cold molecular clouds between stars, often shows water with higher deuterium enrichment. Some researchers argue that part of Earth's water may carry that interstellar signature, meaning some fraction of our water predates the solar system itself. Not all of it, perhaps, but some. And if that's true, it means Earth didn't create all its water. It inherited it. Water formed in dark clouds, froze onto dust grains, drifted for eons, then got swept into the collapsing nebula that formed our sun and planets. And some of those ancient molecules survived the entire process. That concept, survival, is what makes this story feel almost impossible. Because planet formation is violent. Heat, radiation, impacts. And yet, ice can hide. Chemistry can shelter inside grains. Water can be bound in minerals. So the origin story becomes not just about delivery, but about preservation. How water can endure through chaos if it's stored the right way. Now, to connect this to the bigger planetary picture, let's talk about why Earth is different. Venus may have had water, but it lost it. likely through runaway greenhouse warming and atmospheric escape. Mars had water, but it lost much of its atmosphere and protection, and its water froze or escaped over time. Earth didn't just get water, it held it. And isotopes help us see traces of that holding. How water may have been lost, replenished, cycled, stabilized. For instance, atmospheric escape tends to preferentially remove lighter isotopes. So a planet that loses a lot of water to space may end up with water enriched in heavier isotopes over time. That means isotopic ratios can reflect lost histories too, not just origins. So when scientists compare Earth's DH ratio to Venus's or Mars's, they can infer something about how each planet's water evolved and escaped. And that's part why Earth's stable, moderate ratio feels so meaningful. It suggests Earth didn't lose everything. It suggests Earth's water reservoir remained large enough and protected enough to avoid extreme isotopic skewing from catastrophic loss. Now, as we sit with all this, there's a quiet wonder I want to offer you, because isotopes are the opposite of dramatic. They're subtle. A tiny difference in mass, a slight change in a ratio, and yet those tiny differences let us reconstruct billion-year stories. They let us connect the ocean in your glass to meteorites in a museum drawer, to a comet's icy dust, to a diamond inclusion from the mantle transition zone, to interstellar grains drifting in molecular clouds. In other words, isotopes let us travel without leaving our chair. They let us time travel with numbers. And as scientists kept refining isotopic tools, the water story became more textured. Not a single source, but multiple contributing reservoirs. Not a single event, but an era of accretion and cycling. Not a single conclusion, but a narrowing window of plausible origins. And this is where we reach a lovely tension. Because even with all this progress, the water story is not fully closed. Some researchers still argue for a larger nebula hydrogen contribution. Some argue for different mixing timelines. Some explore how early atmosphere chemistry could alter isotopic signatures. Some focus on how deep mantle reservoirs may preserve older water. It's a living question, and that's part of what makes it so beautiful. The ocean isn't just a solved mystery. It's an ongoing conversation between nature and the people trying to understand it. Now, in the next part, we're going to turn from isotopes back toward the planet's grand behavior. How water doesn't merely sit in oceans, but actively changes Earth's geology. How it lubricates the crust, fuels volcanism, enables plate tectonics, and shapes the entire long-term habitability of the planet. Because once water is here, it doesn't stay quiet. It becomes a force. It becomes the thing that makes Earth, Earth. Once water became stable on Earth, once it could pool, persist, and cycle, it stopped being just a substance Earth possessed and started becoming something closer to an operating system. Because water doesn't just sit there. It participates. It pushes. It transforms. It changes how rocks behave, how gases move, how heat is distributed, how the surface reshapes itself over time. And one of the most profound things water may have done, quietly, patiently, over hundreds of millions of years, is help make Earth's surface dynamic. In other words, water may have helped make plate tectonics possible. Now, plate tectonics is one of those phrases we learn in school and then file away like a fact. Continents drift, plates collide, mountains form, volcanoes erupt. But when you really sit with it, plate tectonics is almost unbelievable. Earth's crust isn't fixed. It's mobile. It's recycled. It's constantly being destroyed and remade, like the planet is renewing its own skin. That doesn't happen on every world. Mercury doesn't do it. The moon doesn't. Mars shows hints of tectonic activity, but not the same continuous cycling. Venus, depending on the model, may have episodic resurfacing, but not Earth-style plate tectonics as a stable engine. Earth is special here. And water may be one reason why. Because water acts like a geological lubricant. It infiltrates faults. It gets bound into minerals. It lowers the melting point of rock. It softens the behavior of the lithosphere, Earth's outer rigid shell. When oceanic plates form at mid-ocean ridges, seawater percolates into hot rock and alters it, creating hydrated minerals. When those plates later subduct, They carry that water down into the mantle, and as that slab descends, the water is released. That released water lowers the melting temperature of mantle rock and helps generate magma, which then rises to form volcanic arcs, those chains of volcanoes you see along subduction zones. So water isn't merely being transported. It's actively driving melting and volcanism. And over long time scales, this cycle contributes to Earth's ability to recycle crust, regulate its atmosphere, and sustain long-term stability. Now, think about what Earth would look like without this mobility. A static crust, like the moon's, old, battered, unrenewed. A planet without steady mountain building, without continuous creation of new seafloor, without subduction pulling carbon into the mantle. The carbon cycle wouldn't function the way it does. Climate regulation would be weaker. Habitability would be shakier. So water isn't only helpful to life directly. It may be helping maintain the kind of planet where life can persist for billions of years without the climate drifting too far into extremes. Now, as water altered the crust and helped drive tectonics, it was also changing the atmosphere through chemistry. Because the oceans didn't just exist as a big salty pool. They interacted with rock constantly. Rainwater fell, dissolved gases, became mildly acidic, and weathered silicate rocks on land. This weathering drew down CO2. CO2 then moved into the oceans as dissolved carbon, eventually forming carbonates that got buried in sediments. Subduction carried some of those carbonates back into the mantle. Volcanoes returned CO2 to the atmosphere. That loop, the carbonate-silicate cycle, works like a long-term thermostat. If Earth gets warmer, weathering speeds up and removes more CO2, cooling the planet. If Earth cools, weathering slows. CO2 builds up through volcanism, warming the planet. Water is the mediator here. Without liquid water, you don't get the same weathering. You don't get the same carbon transport. You don't get the same slow, stabilizing feedback. So water doesn't just keep Earth wet. It helps keep Earth temperate. And this temperate stability is part of what made long-term evolution possible. But while all this was happening, tectonics, carbon cycling, ocean chemistry, water was also setting up an environment where life could keep escalating. Because once oceans existed and became stable, they became vast arenas for experimentation. And with time, life began to reshape the water itself. We talked earlier about cyanobacteria and oxygen. Let's sit with the ripple effects for a moment. When photosynthetic microbes began producing oxygen, they changed not only the air, but the ocean. Oxygen reacted with dissolved iron, creating banded iron formations. As oxygen increased, the ocean's chemistry shifted. Over time, oceans became less iron-rich, and the balance of dissolved nutrients changed. Ocean pH evolved. New minerals precipitated. In other words, life and water entered a feedback loop. Water enabled life. Life altered water. And together they changed Earth's surface into something increasingly complex. Meanwhile, water's physical behavior kept shaping ecosystems. It formed rivers that created floodplains. Floodplains became nutrient-rich habitats. Coastlines changed as sea levels rose and fell. Tides created intertidal zones where organisms faced a new kind of challenge, switching between wet and dry. And challenges drive innovation. Even before life moved onto land, these watery edge zones may have encouraged new adaptations, ways to tolerate exposure, to retain moisture, to handle shifting salinity, to anchor against waves. Water doesn't just provide comfort, it provides problems. And problems are where evolution gets creative. Now, zoom out again and you start to see Earth's water not as one thing, but as a choreography. Water evaporates from warm oceans. It rises, cools, condenses. Clouds form. Rain falls. Fresh water flows downhill, carrying minerals and sediments. Rivers deliver those materials to the sea. Some sediments bury carbon. Some get subducted. Volcanoes release gases. The atmosphere changes. Climate shifts. Ice forms, reflecting sunlight. Ice melts, absorbing heat. Ocean currents move warmth around the globe. And through it all, water is both participant and driver. It shapes landscapes. It regulates temperature. It buffers chemistry. It moves nutrients. It sets the stage for life. It is a medium through which Earth's surface becomes alive. Now, when we talk about water regulating temperature, it's not only through greenhouse feedbacks and weathering, it's also through water's physical properties, its remarkable heat capacity. Water can absorb huge amounts of heat without rapidly changing temperature. That makes the oceans a thermal reservoir. They store heat and release it slowly. They smooth out temperature swings between day and night, between seasons, between latitudes, and ocean currents, driven by wind, Earth's rotation, and differences in temperature and salinity, move that stored heat around the planet. This circulation helps stabilize climate patterns. It influences rainfall. It shapes where deserts form and where forests thrive. And it means Earth's climate is not just a product of sunlight. It's a product of water moving sunlight's energy around. Now, this same system can also amplify extremes. When circulation changes, climates can shift dramatically. When ice expands, albedo increases and cooling accelerates. When greenhouse gases accumulate, warming intensifies and oceans change. Water can buffer the planet, but water can also carry the planet into new states. Ice ages, warm periods, global shifts. And life rides those shifts, sometimes suffering, sometimes diversifying, always adapting. So if you step back far enough, the water story becomes less like, how did Earth get water? And more like, how did Earth become a world defined by cycles? Because that's what water introduces. Cycling, not a one-time event, a continual motion, surface to sky, sky to land, land to ocean, ocean to crust, crust to mantle, mantle back to surface. A planet breathing in wetness and breathing it back out. Now, this is the part of the story where Earth starts to feel like a system instead of a place. A living planet. Not alive in the sense of creature, but alive in the sense of dynamic processes sustaining themselves through feedback. Water plays a central role in that. And it's why, when scientists think about habitability elsewhere, they don't only ask, is there water? They ask questions like, is there cycling? Is there long-term stability? Is there a way for the atmosphere to be regulated? Is there a mechanism to recycle carbon? Is there a process that prevents runaway heating or complete freezing? Earth has those mechanisms, and water is woven through all of them. Now, if you're listening to this late at night, you might be feeling that slow widening sensation, like the story keeps growing bigger the deeper we go. Because it does. We started with rain and oceans and comets, and now we're talking about tectonics, climate, evolution. And the wild part is, it keeps going. Because water didn't just shape Earth in the ancient past. It's still shaping Earth right now. Quietly, persistently, constantly. Every time a river erodes a canyon. Every time a glacier grinds stone to dust. Every time ocean currents shift heat across the planet. Every time water seeps into rock, altering minerals. Every time a volcano exhales steam. The cycle continues. Which brings us to something we've been circling for a while. Earth's water isn't just a scientific curiosity. It's a shared inheritance. A finite, ancient system that we live inside. And in the next part, we're going to step into the present moment of the story. How our relationship with water has become not only practical, but moral. Because we're living in an era where water stability, its old reliable cycling, is being strained. Melting ice, rising seas, deepening droughts, extreme floods. The ancient story is still unfolding, but now we're in it, not as observers, as participants. And that's where sleepy wonder turns into something sharper and more tender, responsibility. We'll drift there next. It's easy to talk about water like it's guaranteed, like it's simply part of the deal of living on Earth. You turn a tap, you fill a glass, you hear rain on a roof, you walk past a river, and assume it will keep being a river. And maybe that's why the origin story matters so much. Because once you trace water far enough back, through meteorites, through mantle minerals, through ancient storms and cosmic dust, you start to feel it differently. Not as background, as inheritance. And inheritance comes with a quiet question tucked inside it. What are we doing with what we were given? We live in a time when climate change is no longer a distant theory. It's a present tense reality. Ice is melting. Seas are rising. Droughts deepen, floods intensify, rivers run low while cities grow thirsty. Storms carry more water than they used to. And then, somehow, some regions still burn with dryness. Water's beginning to show us the strained lines in the system. And it's strange, because the very cycles that made Earth habitable, the water cycle, the carbon cycle, the deep cycling between surface and mantle, those cycles are resilient, yes, but they aren't invincible. They run on feedback, on balance, on time. And we are pushing on the balance in ways that are fast. Much faster than Earth usually likes to adjust. To understand why this matters, let's remember something important. Earth's surface water is vast, but usable fresh water is small. Most of Earth's water is salt water in oceans. A huge portion of the remaining fresh water is locked in ice, glaciers, and ice sheets. The fraction available in rivers, lakes, and accessible groundwater, the water we drink, farm with, and build civilization around, is a sliver, a precious sliver. And the water cycle that keeps that sliver refreshed depends on temperature gradients, ocean currents, atmospheric circulation, and stable seasonal patterns. When the climate shifts, the cycle shifts. When the cycle shifts, everything downstream shifts with it. Now, some changes are obvious. When ice melts, sea levels rise. That's already happening. Coastlines redraw themselves. Salt water intrudes into groundwater aquifers. Storm surges reach farther inland. Low-lying regions face an uncomfortable choice between engineering solutions and retreat. But other changes are quieter. Drought isn't just no rain. It's a shift in timing, a change in snowpack, a loss of predictable meltwater, a weakening of groundwater recharge. It's the slow draining of resilience. A region can receive the same yearly rainfall as before and still experience deeper drought. If the rain comes in fewer, heavier bursts that run off quickly instead of soaking in. Water doesn't only matter in how much falls. It matters in how it moves. Floods, meanwhile, aren't just more rain. Warmer air holds more moisture. When conditions trigger storms, that moisture can fall in concentrated, intense events. So you get paradoxes, places that swing between drought and flood, between dry ground and sudden chaos. It's as if the water cycle is becoming more extreme, more jagged, less predictable, and the consequences ripple out into agriculture, ecosystems, human health, and geopolitics. And yet, here's something I want to say gently. This isn't about guilt. It's about perspective. Because when you realize water came to Earth through violence, through impacts and heat and chaos, you also realize that ability is not automatic. Earth's long habitability wasn't just luck. It was balance. It was deep cycling. It was feedback loops operating over geological time. And now, we are changing the atmosphere in a few centuries in ways that usually happen over tens of thousands to millions of years. We've altered greenhouse gas levels. We've changed land cover by deforestation. We've dammed and diverted rivers. We've drained wetlands. We've pumped aquifers faster than they can recharge. We've polluted watersheds with chemicals and nutrients that tip ecosystems into collapse. And still, we expect water to forgive us. We expect rains to return on schedule. We expect snow to keep falling where it always fell. We expect glaciers to keep acting as reservoirs. We expect the ocean to keep absorbing heat and carbon without complaint. But Earth doesn't do guarantees. Earth does systems, and systems respond. Now, here's where I want to shift the tone slightly, not into panic, but into something steadier. Because water also teaches hope if we let it. Not the kind of hope that ignores reality. The kind that comes from understanding that cycles can be protected, restored, and respected. A river teaches patience. An aquifer teaches foresight. A wetland teaches humility. Because a wetland is like an organ, filtering, buffering, holding water during floods, releasing it during dry periods. When you destroy wetlands, you remove that buffering capacity. When you restore them, you rebuild resilience. Forests play a similar role. Trees pull water up and release it through transpiration, feeding cloud formation and regional rainfall patterns. Forests stabilize soils, reduce erosion, slow runoff, increase infiltration. So protecting a watershed isn't just saving nature. It's maintaining the plumbing of a region's water future. And this is where human choices matter. We are the first species to understand Earth's water system in real time. We can measure ice loss with satellites. We can map groundwater changes from space. We can model ocean circulation shifts. We can track atmospheric moisture patterns. We can watch, almost live, as the planet's water distribution changes. That's unprecedented. We are not the dinosaurs, caught unaware by a falling sky. We are the first species that can see the sky changing and know why. That means we're also the first species with a true choice. And choice doesn't have to be grand. It can be practical. It can be collective. It can be quiet. Restoring wetlands. Protecting forests. Reducing pollution runoff. Managing groundwater with long-term recharge in mind. Designing cities that capture stormwater instead of treating it like a nuisance. Improving irrigation efficiency. Supporting policies that prioritize watershed health and equitable access. These aren't just environmental actions, they're water actions. And water is the foundation of everything else. Now, I want to zoom back out just for a moment to the emotional heart of this, because the water story is cosmic and also personal. The hydrogen in your body may have formed in the early universe. The oxygen in your blood may have been forged in a star that exploded long before the sun existed. The water inside you may have been in the ocean when the first fish emerged, when plants first climbed onto land, when glaciers sculpted valleys, when dinosaurs walked, when humans first learned to sail. Your water is ancient, and it's shared. That means when we talk about water resources, we're not just talking about utility, we're talking about belonging. We are water within water, consciousness within chemistry. We are not separate from the cycle. We are a moving part inside it. And that shift, seeing yourself inside the cycle rather than outside it, changes everything. It changes how you think about rivers and groundwater. It changes how you think about pollution, waste, and fairness. It changes what protection means. Because protecting water isn't protecting something external. It's protecting the medium that carries you. Now, there's also a deeper layer here. Justice. Water is unevenly distributed. Climate change amplifies that unevenness. Some regions face severe shortages while others face destructive floods. Some communities have secure infrastructure while others rely on fragile systems. Some nations can adapt quickly while others are pushed into crisis. So the water story is not only ecological, it's moral. Not because nature wants to punish us, but because water reveals inequality with brutal clarity. Who gets clean water? Who gets flood protection? Who bears drought? Who loses land to sea rise? These are human questions wrapped inside a planetary cycle. And they're not optional. Because water doesn't negotiate with politics. It moves according to physics, chemistry, and climate. We just decide how fairly we respond. Now, as we near the end of this part, I want to offer you one quiet idea. Wonder isn't only a feeling. It can be a decision. When you listen to rain on a rooftop and remember it's the same ancient molecule that fell from space, that steam from magma, that cooled the crust and filled the first seas, wonder becomes something active, a way of seeing again. And once you see again, it becomes harder to treat water like it's disposable, harder to treat it like an infinite commodity, because you start to feel the depth of it, the age of it, the patience of it. And in that feeling, responsibility doesn't arrive as guilt. It arrives as gratitude. Now, in the next part, we'll drift back toward the closing shoreline of the story, where everything we've traced converges. Deep time, cosmic origins, isotopes, tectonics, life, and the present moment. We'll gather the threads into one soft conclusion. Not just where water came from, but what it means to belong to a world made of water. So here we are, near the shoreline of the story. We've followed water from cold interstellar clouds to warm oceans, from dust grains to deep mantle minerals, from violent impacts to endless rain. We've watched it become not just a feature of Earth, but a force shaping tectonics, regulating climate, conducting chemistry into biology. And now, after all that distance and time, the question starts to change on us. Because once you understand where water came from, you can't help asking something quieter and deeper. What does it mean to belong to a world made of water? Not just to live on a planet that has oceans, but to realize you are part of that system, literally, that the water in you and the water outside you are not separate things. They're the same ancient inventory, cycling through different shapes and moments. It's strange, isn't it? We spend most of our lives thinking in boundaries. My body, my cup, that river over there, that ocean far away. But water ignores boundaries. It passes through everything. It evaporates and rises, condenses and falls. It seeps into soil, into rock, into roots. It enters cells, becomes blood, becomes sweat, becomes tears. It becomes breath in the form of humidity on the air. And then it leaves again. We are temporary arrangements of water, brief gatherings of an ancient substance that has been moving since before this planet existed. And once you see it that way, the everyday world becomes quietly enormous. A glass of water is no longer just a glass of water. It's the universe's oldest molecule doing its latest job. It's hydrogen from the Big Bang. It's oxygen from dead stars. It's chemistry that survived the furnace of planet formation, the turbulence of bombardment, the slow cooling of a molten world. It's the same water that carved valleys, fed forests, cradled plankton, hosted the first cells. Its legacy held in your hand. Now, if you zoom out just one step further, you realize something else. Earth's water story is not only about arrival, it's about staying. Many worlds may get water. Few keep it stable for long. Mars had water, but it lost much of its atmosphere and protection. Venus may have had water, but heat and radiation unraveled it. Earth kept water liquid and cycling, not because it was destined, but because it had a rare blend of conditions. Enough gravity to hold on to atmosphere and water vapor, a magnetosphere to deflect solar wind, a location in the habitable zone, an internal geology capable of recycling volatiles and regulating climate over deep time. So when we say Earth is a water planet, we're saying something more specific than it sounds. We're saying Earth is a planet where water became stable enough to become a system, and that system became the foundation for everything else, which means the origin question has two answers layered together. One answer is about materials, asteroids, hydrated minerals, interstellar ice, possibly nebular hydrogen. The other answer is about behavior, Earth's ability to retain, cycle, and regulate water. Without behavior, materials don't matter. You can deliver water to a planet and still lose it. Earth's miracle is not just receiving water. It's building a relationship with water, a long, dynamic partnership. Now, there's something else that's easy to miss when talking about oceans as a whole: fresh water. Most of Earth's water is salty and vast, but the part that matters most of daily life is tiny. Rivers, lakes, soil moisture, accessible groundwater. These are fractions of fraction, and they're fed by the same ancient cycle. Rain that falls today may have evaporated from an ocean 3 weeks ago, or risen from a forest, or come from a storm system that carried moisture across continents. Water is constantly rearranging itself, redistributing life's potential in slow and fast ways. And all of it is linked. That means what happens in one part of the system affects the rest. Ocean warming affects rainfall patterns. Deforestation affects regional humidity and precipitation. Melting ice changes ocean salinity, which can affect circulation. Circulation changes climate. Climate changes water availability. Water availability changes ecosystems and agriculture. This is why water is so often the first thing climate change disrupts and the last thing communities can ignore. Now, I want to return briefly to the scientists, because there's a quiet beauty in the way this mystery has been solved. Not with loud certainty, with careful convergence. John Valley Zircon's hinting at early water. Meteorite isotopes pointing toward carbonaceous chondrites. Comet measurements complicating the romantic story. Deep Earth minerals revealing hidden reservoirs. Sample return missions bringing pristine evidence. All of it building a picture that is richer than the old simple idea. Earth's water likely came from multiple sources, but mostly from water-bearing rocky material during formation, with Earth's internal cycling shaping how that water became oceans. That picture isn't as cinematic as comets gave us to see, but it's more intimate. because it means water was present while Earth was being assembled. Water in the planet's bones. Water as part of the recipe. Now, as we draw closer to the end, I want to offer you a soft image. Imagine early Earth again, glowing, scarred, steaming. A sky thick with vapor. Volcanoes breathing out heat and gas. And then, at some point, the temperature drops enough of the vapor to become droplets. Clouds, heavy and endless. And rain begins. Not romantic rain, ancient rain. Rain falling for centuries, maybe longer. Rain hissing on hot rock, exploding into steam. Falling again. Rain filling basins, cooling crust, smoothing rough edges. Rain turning a fire world into a water world. That's one of the most extraordinary transformations we can imagine. A planet learning to hold liquid. And in that transformation, the conditions for life begin to assemble. Not immediately, not inevitably, but possible. Water doesn't guarantee life, but it gives chemistry room to breathe, room to move, room to repeat, room to become complex. And once life arrives, water becomes not just a medium, but a companion. Every cell is a tiny water environment. Every metabolism depends on water's ability to move ions, dissolve molecules, and carry reactions. Life is, in a sense, water learning to organize itself. Now, I want to bring this back to you, because long-form stories like this work best when they land somewhere personal, somewhere quiet, where you can feel it. So here's a simple thought. The water in your body right now is not your water. Not in the way we usually mean possession. It's borrowed from an ancient cycle. It was here long before you. It will be here after you. It has been many things. It will be many things again. A cloud, a river, a wave, a leaf, a snowflake, a tear, and that can feel humbling. But it can also feel comforting, because it means you're part of something continuous. Even in a life that feels short, you're carrying molecules that have traveled through deep time. You are holding the universe's patience inside your skin. Now, in the next part, our second to last, we'll gather the final threads into a closing reflection. We'll return to the original question one last time, but with the full weight of the journey behind it. And we'll end not with a hard conclusion, but with a soft invitation to stay curious, to stay kind, to stay fluid. Let's return gently to the beginning, to that simple question that sounded almost childish at first, almost too obvious to ask. Where did all the water on Earth come from? After traveling this far, through interstellar clouds, ancient meteorites, deep mantle reservoirs, volcanic breath, and billions of years of cycling, you can feel how the question has grown. Because it's not just a question about oceans. It's a question about how worlds are made, how chaos becomes a system, how a planet becomes a home, and how something as ordinary as a glass of water can be a museum exhibit in disguise, holding evidence older than the sun. So, what have we learned? We've learned that Earth didn't start as a calm blue marble. It began hot, violent, molten, a world hammered by impacts, wrapped in thick, choking gases. Its surface a restless ocean of lava. If you could have visited early Earth, if such a thing were even imaginable, you wouldn't have seen beaches. You would have seen fire. And yet, water was there in some form early on, not always as liquid, sometimes as vapor, sometimes locked in minerals, sometimes held deep in the forming mantle, like a secret waiting for the right temperature to be spoken aloud. We followed evidence that suggests much of Earth's water likely arrived not primarily from comets, but from the same rocky material that helped build the planet. Water-rich planetimals and asteroids, especially those related to carbonaceous chondrites. Those ancient meteorites, with their hydrated minerals and their matching DH ratios, make a strong case. And we also held space for other contributions. Possible interstellar water inherited from the pre-solar cloud, and perhaps even a contribution from captured solar nebula hydrogen, later transformed into water inside Earth. So the origin isn't a single dramatic delivery. It's layered, a blend, a slow accumulation during accretion. And then, once the materials were here, Earth's real achievement was retention. Water's journey didn't end when it arrived. It had to survive. Earth had to hold on to it through solar wind, impacts, and intense heat. Gravity helped. The magnetosphere helped. Deep storage and minerals helped. And over time, volcanic outgassing released water vapor back to the surface, where cooling allowed it to condense and fall. Rain began. Rain that likely lasted for ages, turning a steaming world into a wet one. And from there, water didn't stop moving. It cycled. Surface to sky. Sky to land. Land to ocean. Ocean into crust. Crust down into the mantle. Mantle back up again through magma and volcanoes. Earth didn't just get water. Earth built an engine around it, a self-sustaining rhythm. And once that rhythm existed, everything else changed. Water weakened rocks and helped shape tectonics. It fueled volcanism through subduction and melting. It carved landscapes through erosion. It dissolved minerals into the sea, defining ocean chemistry. It enabled the carbon cycle that stabilized climate over deep time. It provided a vast medium where chemistry could become biology, and life, once it arrived, began reshaping water and air in return. Photosynthetic microbes slowly filled the world with oxygen. Oceans transformed. Atmosphere transformed. Complex life became possible, all within the embrace of water. Now, if you pull all these threads together, you get something that feels almost like a secret. Earth's water story is not separate from Earth's identity. It's not a bonus feature. It's a defining trait. Water made Earth dynamic. Water made Earth stable. Water made Earth habitable. And that's why when we look outward toward other worlds, we keep asking about water. Because water isn't just a solvent. It's an invitation to complexity. It's a hint that a planet might have cycles, stability, and enough chemical freedom for something like life to take hold. Now, here's the part we want to linger on before we close, because it's the part that feels the most human. Every drop of water on Earth is part of one connected system. It's been cycling for billions of years. It doesn't belong to any one person or any one era. It belongs to the planet. And you, right now, are part of that planet. Water moves through you. It becomes you. It leaves you. It returns to the sky. It falls again somewhere else. And if that thought lands softly in your chest, it's because it's both humbling and comforting. Humble because we aren't separate from nature. Comforting because we aren't alone in time. We're carried by something ancient. So when you sip water, you're not just drinking liquid. You're drinking an artifact. Hydrogen that began in the first moments after the universe was born. Oxygen that was forged in a star's final breath. A molecule that may have drifted as ice on a dust grain through interstellar darkness. A molecule that may have been delivered in hydrated rock during Earth's formation. A molecule that survived heat, impact, pressure, and time. And now it's here, cool on your tongue. That is the kind of ordinary miracle we forget until a story makes us remember. And now, we can ask the question one last time. Where did Earth's water come from? From dust and rock and ice. From stars and storms. From the building blocks of planets. From deep Earth chemistry. From a long partnership between gravity and time. But maybe the more meaningful answer is this. Earth's water came from everywhere, and it stayed. And because it stayed, Earth became a world that could hold life. Now, in our final part, we'll step onto the very last shoreline of this journey. We'll end the way long-form stories like this should end. Not with a lecture, but with a quiet farewell. A closing that feels like rain fading on a rooftop. A reminder that the wonder isn't just out there in the cosmos. It's in the cup beside you. So here we are, at the end of the current, where the story widens into stillness. We started tonight with a question that hides in plain sight. A question so ordinary it feels almost silly to ask until you realize it isn't ordinary at all. Where did all the water on Earth come from? And now, after traveling through deep time, through space, through stone, through storms, the question feels different, like it's wearing a deeper meaning than it did at the beginning, because the answer isn't a single place. It isn't one comet, one impact, one moment of delivery. It's a braided history, a chain of chemistry and chance, of survival and cycling, of a planet learning, slowly, how to hold something fragile. Earth's water came through the early solar system's mesocollisions and drifting material. It came packaged in hydrated minerals, carried by planetimals and asteroids, echoed in the signatures of carbonaceous chondrites. It may have carried traces older than the sun itself, ice inherited from interstellar clouds. It may include hydrogen captured from the solar nebula, later transformed inside the planet. It came in pieces, in whispers, in grains of dust and rock. And then Earth did something remarkable. It kept it. It held on to it through the furnace years, through bombardment, through solar wind, through the long cooling of a molten surface. It stored water deep in minerals. It released it through volcanism. It let vapor condense into clouds. And when it was cool enough, it let rain begin, rain that likely fell for ages, turning fire into ocean. And after that, water didn't just stay on the surface. It started moving in loops that shaped the planet into what it is. Water helped weaken rocks and make the crust more mobile. It lowered melting points and fueled volcanism. It participated in the deep cycling of subduction and outgassing, water down, water up, earth breathing wetness in and out. It carved valleys and wore down mountains. It carried minerals into the sea, shaping ocean chemistry. It enabled the long carbon cycle that helped stabilize climate. It became a medium where chemistry could stretch, combine, and eventually awaken into life. And life, once it arrived, began reshaping water and air in return. A planet and its water, changing each other over billions of years. That's what makes Earth's oceans so much more than scenery. They're an engine, a memory, a system, a living archive. And now, here in the present, the story continues, not in ancient eons, but in daily movements so familiar we barely notice them. Water rises from the ocean as invisible vapor. It gathers into clouds. It falls as rain. It runs downhill, feeding rivers. It seeps into soil. It nourishes roots. It becomes sap in fruit and leaf. It becomes sweat and breath. It becomes snow, ice, fog, mist. It becomes the sound of a shower, the weight of humidity, the taste of tea. It becomes the quiet ache of drought and the roar of a flood. It becomes every kind of weather that ever touched your skin. And because Earth is largely a closed system for water now, because most water doesn't truly leave in significant amounts, every drop you touch is part of one shared inventory. The water inside you right now has been somewhere before. It has belonged to other eras. It has cycled through forests and oceans, through glaciers and storms, through animals and plants, through ancient seas under alien skies. It's been a cloud and a wave and a river and a tear. And someday it will be again. That's the soft, strange comfort of water. It doesn't care about the boundaries we draw. It flows through them. It makes a continuity where we tend to see endings. So maybe the real gift of learning where Earth's water came from is not just a scientific answer. Though the science is breathtaking, maybe the gift is that it makes your world feel newly alive. Because suddenly, you're not just standing on Earth. You're standing inside an ancient cycle. You're not separate from the oceans. You are a temporary gathering of them. Water within water. Life within chemistry. Consciousness riding on molecules older than the sun. And once you see that, wonder becomes harder to lose. Even on an ordinary day. Even when you're tired. Even when life is loud. You can still hear it, if you listen closely. The old story in the simple things. The hiss of rain on pavement. The hush of waves at night. The quiet weight of a glass in your hand. So, the next time you drink water, really drink it, try to remember what you're holding. Not just hydration. Not just a resource. A traveler. A survivor. A molecule that has crossed deep time to arrive in this moment with you. And if you want to turn that wonder into something real, something active, you can, because water's story isn't only cosmic. It's also moral. We live in a time where water stability is being strained. Melting ice, rising seas, shifting rainfall, deepening drought. The ancient cycles are still strong, but they're being pushed fast, and feedback loops don't always respond gently to sudden pressure. So caring for water, protecting watersheds, restoring wetlands, reducing pollution, sharing fairly, isn't just being practical. It's participating wisely in the story. It's honoring an inheritance that took billions of years to assemble, not with guilt, with gratitude, with care. with the understanding that wonder isn't just something you feel. It's something you choose again and again to see the miracle in the mundane. Thank you for drifting with me tonight through Earth's oldest question. If this story stirred something in you, a thought, a memory, a ripple of curiosity, feel free to share in the comments. I'd love to know what water means to you. And if you like more slow, deep, quietly scientific journeys like this, you're always welcome back here at Sleepy Earth. You can like the video, subscribe, or share it with someone else who might need a calm story to carry them downstream. Until next time, stay curious, stay kind, and stay fluid.